In late July 2025, a wave of attention turned toward one of the rarest objects ever to cross our skies, the interstellar comet 3I Atlas. We've got some fresh images of 3I Atlas. 3 Atlas. 3 Atlas. 3 Atlas. Some of the world's most advanced observatories, including Hubble and the James Webb Space Telescope, had locked onto it, capturing data that hinted at something extraordinary. Its coma was swelling to immense proportions. Strange fluctuations in brightness were being reported, and amateur astronomers began to note a faint green glow around the nucleus. For a brief moment, the story of 3 Atlas seemed poised to capture the world's imagination. Then the stream of official updates slowed and soon after stopped entirely. NASA and its partners attributed the sudden pause to solar viewing constraints and instrument safety protocols. But for many observers, the silence felt striking. When earlier interstellar visitors such as Oumuamua and Borisov were discovered, the flow of data was fast and public, feeding excitement and debate. With 3 Atlas, the blackout left behind a vacuum. And into that vacuum rushed speculation about what had been seen, why nothing more was being released, and what questions still linger about this elusive comet from beyond the stars. On July 21st, the Hubble Space Telescope captured some of the sharpest images of 3 Atlas to date. Just over 2 weeks later, on August 7th, those images reached the public, showing a small nucleus only about 5.6 kilometers across, but surrounded by a vast dust plume stretching sunward. Meanwhile, the James Webb Space Telescope had taken its turn, pointing its near-spec instrument at the comet on August 6th. Expectations were high that Webb's unprecedented sensitivity would deliver breakthrough insights. But when details emerged, they came only as dry technical notes and cautious preliminary comments. No vivid headline images accompanied them, only suggestions that deeper analysis was underway. Later in August, Gemini South in Chile contributed its own set of images, confirming 3 Atlas's activity and tracking the evolution of its tail. Those data entered public archives in early September, sparking another wave of online discussions. Yet soon after, the pace faltered. Past September 22nd, there were no new flagship telescope releases. Hubble, Webb, Gemini, all fell silent. For those following closely, the gap was glaring. The explanation lies in the unforgiving geometry of space. Observing with Hubble or Webb is not as simple as turning a telescope toward a bright point in the sky. Both observatories are governed by solar avoidance rules, strict limits designed to prevent stray sunlight from damaging their sensitive optics. For Hubble, the cutoff is 50 degrees from the sun's position. For Webb, the requirement is even stricter at 85 degrees. These values are hardwired into the observatory's planning tools. As 3 Atlas moved along its orbit, its solar elongation steadily shrank. By late August, the comet had crossed both thresholds. Hubble reached its limit shortly after July's images, while Webb managed its August 6th run just before the cutoff. Once 3 Atlas drifted inside those angles, the telescopes entered automatic blackout. Observing was no longer permitted, and no override was possible. Any attempt to schedule such an observation would trigger safing protocols that could shut down operations until a review. The silence was not deliberate secrecy. It was physics. That silence, however, coincided with tantalizing hints from the data already collected. Hubble's July images revealed a coma nearly 348,000 kilometers across, greater than a quarter of the sun's diameter. Such a scale is extraordinary, far larger than most comets at similar distances from the sun. Spectroscopic notes hinted at something stranger still, a possible dominance of carbon dioxide in the coma. If confirmed, this would be a profound clue about 3I Atlas's origins. Most comets within the solar system display water as their dominant volatile at this range. A CO2-rich composition could point to very different conditions in the comet's birth environment far beyond our system. Though no peer-reviewed paper had confirmed this as of late September, the whispers lingered and scientists did not deny the possibility. Ground-based observers quickly stepped into the void left by the silence of Hubble and Webb, and their efforts became the main thread of 3 Atlas's story. Night after night, telescopes in backyards, university observatories, and regional survey facilities tracked the comet's progress across the sky. What they saw was both familiar and puzzling. Reports consistently described a greenish tint spreading through the coma. This kind of glow is not unusual. Molecules such as dicarbon C2 and cyanogen CN often flues green when excited by sunlight, and many comets display the effect. Yet, in the case of 3 Atlas, the green seemed uniquely bright and oddly persistent, hanging on from observation to observation in a way that defied easy comparison with previous comets. Without spectra to confirm the chemistry, the exact cause remained uncertain, but the visual impression was striking enough to stir debate. The comet's plume, first identified in Hubble's July images and later captured again by Gemini South, also became a point of fascination. Unlike the broad, steady tails of many comets, 3 Atlas's plume appeared changeable. On some nights, observers reported a sharp, well-defined sunward spike. On others, it looked diffuse, less distinct, or skewed to one side. The brightness also seemed to vary, occasionally flaring before fading back again. To some, these variations pointed to jets or outbursts on the nucleus, localized vents releasing gas and dust in sudden bursts. To others, the changes were nothing more than shifts in geometry as Earth's viewing angle altered the appearance of dust streams. The lack of flagship data left no way to settle the argument, and so the plume became a mirror for competing interpretations. Photometric measurements added a further layer of complication. Observers around the world tried to track 3 Atlas's brightness, but their results often failed to align. Amateur astronomers using modest telescopes and CCD cameras posted estimates that sometimes differed from professional-grade observations by more than a full magnitude, a factor of more than 2 in brightness. Such discrepancies are common to some extent. Differences in calibration, sky conditions, and equipment can easily skew results. But the scatter for 3 Atlas seemed unusually large, and in some cases, even individual observers reported fluctuations from night to night that were difficult to explain away as simple error. The possibility emerged that the comet's brightness was genuinely unstable, flickering as activity surged and subsided on short time scales. As September gave way to October, the lack of new data began to feel personal for those who had invested time and passion in tracking the comet. Social media threads filled with frustration. "It's like chasing a ghost," one amateur astronomer wrote. "Every night we're guessing what's actually happening out there." Another demanded, "Why can't we just see the raw data? What are they waiting for?" The reality is less sinister.